Hello, I'm Sam Bose. I'm a PhD candidate at the University of Alabama, and I'll be talking about the results of my first paper published last year, along with its follow-up paper regarding some double detonations in thin-shelled white dwarfs that theoretically produce a Type 1a supernova. So we've already heard a lot of good stuff about the background of Type 1a supernovas already today. But as a little background, Type 1as are extremely important for a variety of interests in astronomy, most famously in cosmology, where supernovas are integral to the distance ladder, as well as the discovery of the accelerating expansion of the universe. However, it can be somewhat alarming to people who rely on observations of Type 1as that we ultimately don't really know exactly where these extremely luminous events are coming from. As we already heard today, we are very confident that these Type 1as come from explosions in carbon-oxygen white dwarfs, driven by some mechanism in a binary, but the exact configuration of this binary system and how exactly this white dwarf explodes is still a mystery. So being able to use theoretical modeling to predict the synthetic observables from various different candidate progenitor systems or explosion mechanisms can really help to understand these events and their uses across astronomy. So the explosion mechanism that I work on is called the double detonation, where you have a helium shell surrounding some carbon and oxygen white dwarf with some helium-rich companion. This helium shell is ignited in some way. The helium detonation wraps around the core, the carbon-oxygen core. This detonation of the helium shell sends a converging shock into the core, which converges a little bit off-center and triggers a full detonation of the carbon-oxygen white dwarf. So here's a video of that. This is in temperature, where red is hot, so you'll be able to see where the detonation is traveling. Out here is the helium shell. Down here is the carbon-oxygen white dwarf, and these contours are in density, so you should be able to see the shock that's traveling inwards as the helium shell detonation goes around. So that's the helium shell detonating, sends a converging shock into the core, which converges and triggers a complete detonation of the white dwarf, which theoretically is producing a Type 1a supernova. So the double detonation has been around since about the 80s, and has gone through some ups and downs in terms of its viability in producing normal Type 1as. But generally, it was previously thought that the double detonation scenario doesn't contribute to normal Type 1as because the minimum helium shell that you need for a detonation to propagate that helium shell is too large, such that you get significant amounts of nickel-56 and other heavy or radioactive elements that led to light curves and spectra that don't match normal Type 1as. However, Kromer et al. 2010 showed that if you just simply remove these ashes from this helium shell, that's what's left is something that pretty decently reproduces a Type 1a supernova. This study also crucially showed that if you enrich the shell with some underlying carbon-oxygen that might get dredged up a little bit during accretion, that this carbon-oxygen enrichment can also limit the adverse effects, limit the burning in the helium shell and limiting the adverse effects that correspond with these large helium shells. Additionally, a few laters, Shen and Moore, showed that when you use a much larger or a very large nuclear network, you have a helium shell that's polluted with carbon, oxygen, and a crucial isotope of nitrogen, that actually your threshold mass to propagate a detonation in the helium, that threshold drops about an order of magnitude, significantly dropping the mass that you need to propagate a detonation, providing some hope that these lower mass helium shells could lead to normal Type 1as. So all of this and many other good works in the past 10 or 20 years or so inspired the work of my advisor, Dean Townsley, and others in 2019, where they conducted a single simulation of a thin shell detonation in a 1 solar mass white dwarf and produced some observables from it. So here is spectra. In gray is supernova 2011 FE, and these different spectra in different colors are the spectra from that one detonation study. And because that study was in 2D, we have spectra from different lines of sight. And with the correct choice of line of sight, you can find a spectra that decently matches an observed supernova. And this was an interesting result, that you can have some consistent double detonation that normally detonates in simulation and producing observables that look normal without doing anything too funny with it. However, there was only one model examined in this study, which kind of begs the question about how the double detonation scenario looks across a range of progenitor configurations. And this is important because there is this large diversity in type 1As. And so this is kind of a map of the observational diversity of observed type 1As. So on this y-axis here, we have the peak absolute B-band magnitude, which is how bright it gets. And then the x-axis here, we have silicon 2 velocities, which are somewhat of a representation of spectral variety. And as you can see in the gray, where observed supernovae are, there's a great diversity, not only in their brightnesses, as we know, but also their silicon velocities. So being able to explain some subset of these diverse events through modeling could be a good thing. And as a little tease for our final results, plotted over the top here are, in different colors, are the results from different masses, and then in different shades are at different lines of sight. And in general, across all our masses across all our progenitors that we use are observables that correspond with those progenitors generally reproduce the great diversity seen across all type 1As. So just a little bit about how we got there. And so in Bose et al. 2021, Chen et al. 2021, we present some 2D double detonations in carbon and oxygen white dwarfs and produce their observables. These progenitors range in both core mass and shell mass. Most of them are these thin shell cases with shell masses on the order of a 100th of a solar mass, but we do have a couple of fixed shell cases for comparison. We use the multiphysics code Flash to carry out these 2D simulations, and we also use the burn routines from the stellar evolution code MESA. We use a burning limiter, which allows us to better resolve some of these detonations that would otherwise have extremely small burning length scales. Additionally, we also use a relatively large nuclear network of 55 isotopes, and also go back later and post-process with an even larger nuclear network. And then lastly, we use the 2D radiative transfer code Sedona to generate light curves and spectra, and we do use the LTE assumption. Okay, so here's the video again, just to show you what a typical double detonation looks like in one of our simulations. So again, helium shell, carbon oxygen white dwarf. The helium shell is ignited with an artificial hotspot at the interface of the carbon oxygen white dwarf and the helium shell. So that triggers the helium detonation. Sends a converging shock inwards that notably converges off-center. And that triggers a full detonation. So this is essentially what all of our detonations look like across all of our dozen or so models. And at the end of each simulation, what's important is not only how much material is produced, but at what velocities they're produced, because those two things ultimately decide what your observables will look like. And this is just kind of a raw look at what the outcomes of all those simulations are. But we can't really compare them or think about them too much until we look at the observables. So the most obvious thing to look at sorry, I just froze, I guess. But the most obvious thing to look at when trying to evaluate these models is their spectral properties. So here is a comparison at max light. Here in the gray is spectra of max light of supernova 98 BP. And plotted over the top of that is results of our 0.9 solar mass thin shell case at different lines of sight. And as you can see that at the right choice of line of sight, for this case, somewhere near mid-latitudes, it's a pretty good match for 98 BP. But then looking at other masses, so looking at the low luminosity model, again, we have a pretty good match around mid-latitudes for supernova 99BY. And then in our high mass case, we have a pretty good match for 99 DQ at lower latitudes, southern latitudes. So the spectrum looks good. And looking back at this kind of diversity map, we can see that not only from what I showed in the spectra, our events are spectrally normal, but also reproduce the diversity in observed type 1As, which is a pretty exciting result. However, not everything's perfect. There are still a few issues with our models. Most notably, our models are too red compared to observation, but this is an issue throughout a lot of type 1A and supernovae calculations because the LTE assumption in these radiative transfer calculations has been shown previously to lead to over-reddened results. Additionally, our silicon velocities, especially for our high mass models, are a little bit higher than what's observed in reality. One idea that Ken had for this was that in our simulations, we're only simulating the primary detonating star, but theoretically, like we talked about before, there would be some companion that could theoretically maybe absorb some of the energy where those high silicon velocities are. But this brings up a bigger question of what ultimately happens to the companion and what the effects of these are. So there's been a lot of good work on this in the past 10 years or so, but recently piqued my interest was we talked about earlier, is this paper Packmore et al. 2022, where they conducted a couple 3D simulations of double detonations in a primary and a companion, and they showed that following the helium shell and primary core detonation, this can actually trigger a helium shell and white dwarf detonation in the companion as well. So you get a double detonation. And they actually showed, as we saw earlier, that when you have this detonating second star, that actually it doesn't really affect the spectra too much, which is a really interesting result. However, in their work, they only used, their companion that they used was low mass and presumably didn't really make much radioactive material. So that could give you the idea that maybe you're able to hide this non-radioactive core in there without having any effect on that. So this inspired me to do a series of my own double detonations with a companion in 2D. So this is right here is a video of nickel generation being generated over time in one of these simulations. So at first what happens is a bunch of nickel is being generated in the core of the primary, which is normal. This is what you would see in an isolated double detonation. So you have a discrete core of nickel being generated, that's normal. But then shortly there's a delay, and after the double detonation of the companion, you have an impact on the primary ejecta from the companion ejection. And at first, looking at this ejecta, you would think that maybe there's no way that this would look normal because you're severely impacting the ejecta, not only the amount of nickel, but also the distribution of the nickel. But the really interesting result we get is that actually this looks, both in spectra and light curves, looks similar to our previous work and also to observation. So here in black is observed supernova 98 BP. In red is our previous isolated double detonation case. And in green is a double detonation case where you have two stars explode, and both have some differences, but for what data we have, the spectra at max light both are able to decently reproduce 98 BP. So this is an interesting result, but obviously demands some more investigation with the fact that you can have a second detonating star that has little impact on the observables. So thank you.
Thank you, Sam. Questions?
Hey, nice talk. When you say thin shell, is that the same thing as saying dynamically driven mass transfer, or could any of these be the product of stable mass transfer?
So yeah, so like the idea that I have for a thin shell detonation, for a thin shell detonate would have to be in some dynamic transfer scenario, as I know it. But I take the easy way out and don't consider how this shell was built. I just put it there. So.
Hi. This is the second time I've seen your new stuff, and so sorry if I'm asking a question you haven't done yet already. But we know when we have 1As with bimodal nickel distributions, we end up with things like bumps in the light curve. Do you see that ever, or just not from given line of sights, or?
No, we don't. We do not see significant bumps, which is something that, I'm sorry, I think I have some companion light curves. Yeah, so this is just in V band. But no, we don't see any like B band. Sorry.
Do you know why that differs from just having nickel on the outside?
No, because when you look at this, no, I'm not totally sure. Because when you look at this, for people who are familiar with the fixed shell detonations, this is kind of what the distribution of nickel would look like when you have a fixed shell detonation and a core detonation. You have these kind of two regions. This is the kind of stuff that leads to a lot of like line blanketing and stuff that's not observed in normal type 1As, but we do not get that with these 2-star detonations. So it's something we're still figuring out.
Okay, so in the last spectrum you showed before your conclusions, it looked like there was one difference.
Yeah, right at the
short wavelengths.
Yeah, about 4,000 or so.
That calcium, what is that? Yeah.
Yes. Yeah, that ideally could maybe be a way of, if theoretically you have double detonations in reality occurring with 1 star and 2 stars, that maybe something like this could be a way to kind of decipher between the two. Yeah, but it's not something we've looked into too much. And these differences are, I've only showed like one model, but these differences are very dependent on what the companion mass is too. Sorry, so this is kind of what the ejecta looks like with a 0.85 plus a 0.8. You get this like very asymmetrical kind of distribution. But then if you have a more massive companion, it kind of makes it more symmetrical.
So do you know what that line is, around 30?
Oh, sorry, you asked me.
I'm just curious what.
No, I mean, I would probably say calcium like you guessed, but.
It looks like the new models fit better, at least to that one super.
Yeah, there are many features that the new stuff does look better. Though in this one, the singular case matches that line better. But.
Thanks.
Hi, great talk. I was just curious, in your plot that you show like your masses due to observed, yeah, that one. So you said the higher ones could depend on the companion, but it looks like the lower ones didn't match super great to the supernova.
Yeah. So you mean like these lower mass ones?
Yeah.
So yeah, those are off observation. But there's a big gap between this 0.9 and 0.85 case. So maybe if we did like if our lowest mass model was like a 0.87 or something, like maybe it would lie here. And this may show that there is some like mass threshold for having these double detonations. Because if your 0.85 actually can't double detonate in reality, then you wouldn't get observations down there.
Okay, so are you pretty confident that it's from just like an intermediate mass, or, I mean, you said the companion would absorb energy, right?
Yeah, well, sorry, for that I just meant that with the silicon velocities.
Okay.
So with the silicon velocities, these are at northern latitudes, so back up so the silicon velocities that are high are towards this direction. But in my simulation, I didn't have this companion. So if this companion survives and this ejecta impacts the companion, that maybe that could absorb some energy and slow down the silicon. Early results show that actually doesn't really affect the velocities that much. But
thank you.
Yep.
Okay, we're almost out of time. Do you have a quick question? Okay.
Hi, great talk, Samuel. Chris Nee here. Because you have such thin helium shells, it tends to be on the very outside of the ejecta, which means that it'll be present in like the very early light curves. I was wondering, how early can you put out observable predictions from your multidimensional models?
That's a good question. I mean, you mean like how early how early does our theoretical light curves go?
Yeah.
I mean, I don't think there's a limit to that as long as these are Monte Carlo simulations. So I think if you would include enough particles or whatever, you would be able to generate observables at any time, early time, I would think.
So for like a 1% helium shell, for instance, that would go to like before 1 day. Do you have like predictions over first hours?
Yeah, I suppose you could do that, yeah. I don't know what observation I would compare that to, but
Well, okay.
yeah.
All right, let's thank our speaker.